So yeah, like you said, I think some of this is AP pre-calc stuff, but we are going to extend it into calculus. Okay, so when we talk about maximum and minimum values, there's a lot of information here. But I'm going to try to simplify it as much as I can for you. Okay, and like I said, I provided most of this for you already. So when we talk about extreme values, sometimes known as extrema, okay, we are talking about really four things, but there's a relationship between all of them. First off, we have an absolute maximum, sometimes known as a global. So if you see that phrase, global maximum, it's the same thing as absolute maximum. All it is saying is there's some value C, some X value, where it's the highest point on the graph it's going to be. And that Y value that's associated with that particular X value is the actual maximum value. Now, back in Algebra 2, when we talked about parabolas, we learned about a maximum and minimum value. Those are always the y-coordinate of the vertex, right? For these types of situations, you're going to have some kind of curve, and if there is an absolute or global maximum, it will be where the y value is the absolutely highest number that you could get. It doesn't have to happen in one place. It can happen in multiple places, okay? Then, of course, we have an absolute minimum value or a global minimum. And that just means the lowest value, the lowest y value of the entire curve anywhere, and the lowest y value, the smallest y value. Those are pretty straightforward. It could be called a global, could be called absolute. The ones that are a little trickier, I guess those are on the next. Did I skip them all together? I don't know. Let's see. There we go. Okay, so it is important to understand that these things can happen where there's a horizontal tangent. They can happen where there's a cusp, okay, and I know most of the time we call a cusp a sharp turn. It can happen at a jump. Or they can happen at endpoints. All right, the other part to think about here is we can have what's called local extrema, okay, or relative extrema. And what this means, here's a way to kind of think about this. First off, it's got to be on an interval. So if you look, one of the phrases that we like to use in calculus is that in a particular neighborhood, there could be a minimum value or a maximum value. But that doesn't mean it's the maximum of the entire curve or the entire function. It just means in that particular window. What's important is the only way that we can define a local minimum or a local maximum or a relative minimum or relative maximum is that it has to be contained within an interval. It can't be an endpoint. So notice that distinction. It can still happen at a horizontal tangent. It can happen at a jump. It can happen at a cusp or a sharp turn, but it cannot be an endpoint. It has to be contained within an interval. Okay, and so I've given you some graphs, okay, and I don't want to spend a lot of time on this, but what is the highest value of this graph overall? 5, right? Right here, the highest value, so this is the absolute maximum. Could this also be viewed as a relative maximum? Like if I looked at just a particular window, a particular neighborhood on some interval, okay, it would be the highest value in that interval. So an absolute maximum and a local maximum can be the same thing, right? Now, can this point here be a local max or min? Can it be an endpoint? The answer is no, it cannot. It cannot be a local max or min. It can be an absolute because there's nothing on this side of it. Remember, it has to be contained within an interval. Okay, so if I decided to zoom in on this area right here, I could find a local, but not here because there's nothing on the right side. Not here because there's nothing on the left side. It has to be contained within an interval, so there has to be something on both sides of it to be a local. Now, what is the minimum value going to be for this one? 2, right here. Okay, that could also be a local minimum if I was looking at just that window. Okay, so keep that in mind, that a local min or max has to be in the middle of something. Okay, in whatever window that is. Now, here's another example. Okay, so we've already shown what the max and the min are, right? We have a maximum here where at x equals d and f of d, we have a absolute minimum. But for example, if I zoomed in and I only wanted to look at this window right here, okay, what would be happening at B? Relative max or local max, okay? And then because on either side of it, there's nothing bigger than it. Okay, I could look at another window. Let's say I looked at this window right here. Okay, what's happening at E? Relative minimum or a local minimum. It's not an absolute minimum because I have this one that's smaller.
But is that an endpoint?
Here?
No.
Right, so that's why it can be an absolute, but it can't be a local. Okay? Absolute or global minimum or maximum can be endpoints. Locals cannot. Okay, those are some examples. So this is a way to look at it. And that's what I was trying to do kind of with the highlighting. Make sure that there's something on either side to be a local. Okay? And so, like I was saying before, you could have both in one spot, but an endpoint can't be both. An endpoint can only be a global. It cannot be a local or relative. Okay? All right, let's keep moving. The extreme value theorem. Okay. If f is continuous, one of the things I will tell you on the exam on an FRQ is that there are these conditions that need to exist in order to apply some of these theorems, not just this one, but for other theorems that we will look at going forward. It is very, very, very important that you state whether or not those conditions are true and are met, because that will be a point. I can tell you for sure that on the FRQ that I graded last summer, a point was issued for stating a condition. If you didn't state the condition, you didn't get the point. All right, so the extreme value theorem says if f is continuous on a closed interval, AB, closed, meaning A and B have endpoints. So this curve, this interval has endpoints. Then f attains an absolute maximum value, f of c, and an absolute minimum value, f of d, at some numbers. Somewhere along the way, if it's a closed continuous curve, there's going to be a max and there's going to be a min. That's all it's saying. Okay? So what I want you to do with this graph that you have in your notes is I want you to identify all the absolute and local minimum values and absolute and local maximum values. You can say, actually, I would like you to say, I'd like you to say what the x value is, where it occurs, and also what the maximum value or minimum value is. Does that make sense? Okay, do that quickly, please. Thank you. All right, let's start with the absolute minimum. And you can write it lots of different ways. First off, what is the y value?
0.
Where does it occur?
2.
Okay, so the absolute minimum is 0, and it occurs at x equals 2. Does it occur anywhere else?
Nope.
No. So that's how I would want you to write it, something like that. You wouldn't necessarily have to write it as a, titled in the underline and write it underneath. You could put like a colon after, put f of x equals 0. I mean, that's probably a better way to do it. F of x equals 0 at x equals 2. You could say f of 2 equals 0. Any of those things mean the same thing. But so I want you to communicate that to me as you do that. So go ahead and finish those. All right. So, all right, we've talked about this point now here. This is our absolute minimum. How about absolute maximum? What's that going to be?
5.
1, 2, 3, 4, 5. Absolute max? Isn't it that?
Yeah, that's it.
Oh, I thought somebody said something about 3. Oh, okay. 1, 2, 3, 4, 5, 6, 7, 8. What do we think this is? Very good. Okay. So, all right. So we got absolute max or global max, same thing. So f of 8 equals 5. Okay. Or you could say 5, x equals 8. It's fine. All right. Can this be a local minimum?
Yes.
No.
No.
One of those is correct.
No.
No, why not?
Because there's nothing on both
Nothing
sides.
on the left. How about this one right here?
Yes.
What is this? Relative max, local max at 1 equals 2. This one, local max or min? Max at 4 equals 4. Local max or min? Min at 5 equals 2. Local max or min? Max at 6 equals 3. And how about this one? Can this be one?
Yes.
Yeah, sure it can. Okay. Even though it's a cusp and it's not differentiable here, we can say that. What is that? 6, 6 and 7, 1? Did I count? Was that not supposed to be 8? 1, 2, 3, 4, 5, 6, 7, 8. No, there's just one here that I don't need. Sorry, 7, 1. All right. You guys get that? We're good? Counting, it's important. All right. Now, go ahead and do this one. You have this already on there. I want you to fill in the blanks. No, there's no blanks. Just answer the questions. Do we have any dilemmas here?
The one with the white dots.
The white dots.
That's allowed.
The open circle, thank you.
Circle, thank you.
Okay, we'll get to that one here in a second. All right, absolute maximum F. Easy enough, right? What is it? 4, right? That's that point up there. 4. At what x value does F have an absolute maximum? So now we're just saying, what's the x value that goes with that? And so F equals -4. Point. And number 3, what is the absolute maximum point? So then you just put those together. -4, 4. All right. So here's our dilemma for 4.
Wait, how? Oh, never mind. So
Okay.
sorry.
All right.
Just do parentheses.
It's a point.
Well, so let's get to that. Where would we go to find the absolute minimum? We think it should be here, right? But there's no point here. That's why it's an open circle. So you go, okay, well, I'll just scooch a little bit above it. So what would that be? Negative 1.9 repeating is -2.
Oh, negative. Yeah.
Right? Negative 1.9. You can't. And then you have to stop. And then somebody else will add another 9 on it. So that doesn't work. Because then somebody else could add another 9 on that. So what is the answer for number 4?
-2.
No.
It says they exist.
Can we like say the limit
No, it
of
doesn't.
it is like
Yes, it does.
No.
-2?
Absolute extreme exists at horizontal tangents. but-
-2.
Oh. No, it's on the nose.
No. No. There is none. There is not an absolute minimum. Because we cannot, hold on, because there would be, it could happen there. It doesn't mean that it does happen there.
Oh.
It doesn't mean it does, it means it can happen there. There is no minimum value, there is no absolute minimum. Because for every single person that would say -1 point and however many 9s you feel like you can write down before you die, someone else will outlive you and add another 9. And then another 9. And then another 9. Okay? And so when that happens, because now sometimes there might be a spot lower, right? But on this graph, there is nothing lower than one of these points down here.
So why not say 1 point equal?
Because that equals -2.
Well, actually.
It does. Well, I'll prove it to you later, but it does. Now, so here's the answer. The answer is when this situation happens, there is not a absolute minimum or maximum if it happened to be up there. So if it would have been up here, the same thing would have been true. Okay. Now, local minimums. Okay, so that's when you're looking at windows. You're peeking at windows. Okay, so you should have had 3 of them. You should have had 3 of them. Okay, and you might be thinking to yourself, well, wait a minute. Why is it this one? What about? Okay, it's the same reason. Remember what a minimum or maximum is. It is the Y value. So if I extended that highlighting upward, that you could see that window. Okay, so those are my 3. And the question is, what X values have a local minimum? So it doesn't ask us for the actual minimum values. It asks me for just the X values. And so that is -3, 1, and 2. And then local maximum. Okay. Can 4 be?
Nope.
Can this be a local maximum? No. Okay. This one, and I don't have a point here, so there's only one. Okay. But even though I highlighted both of them, but there can only be one at X equals -1. Keep moving. All right, so this is in your notes too. Critical numbers. We've talked about critical numbers or critical values. A number C in the domain such that the derivative at that value equals 0 or it does not exist. Okay? It's one or the other. So critical values, critical numbers. So this is where we diverge away from the pre-calculus notions of maximum, minimum. And I think you've talked about concavity, concave up, concave down, yes? In pre-calc. We're going to connect that to calculus now. All right? We have this theorem called Fermat's theorem. I thought about even having you come up and draw on the board, just to prove to you that this exists. This is true. If, okay, you can do it. Okay, if F has a local minimum or maximum at C, and there is a derivative at C, then that derivative has to equal 0. Okay, let's think about a picture. Say it again. Horizontal tangent, because the slope of that tangent line is 0.
How does he do it?
So what is being said here is this. If you have a local min or local max, okay, then at that, and it's differentiable, meaning it's connected and there are no sharp turns, then the derivative has to be 0 somewhere. And it has to be 0 wherever that local min or local max is. Okay? And so that's what this is saying. That means you have a horizontal tangent. I was thinking of a different lesson. Maybe that lesson I'll have you draw something. That's going to be 4 too. That'll be Monday. Which Monday's going to be tricky because we have math. So I might have to make a video because I think we might get cut off Monday. We'll see. I don't know. All right. So here are examples. Find the critical numbers of each function. So this means you have to consider one of 2 things. Okay, bless you. The first thing that I would do, honestly, is see if there's any spots where it is undefined. Okay? So on problem A, is A ever undefined? No, I can plug anything in for it. So then, from that point, I just take the derivative. So I don't have to worry about any critical numbers where it's undefined. Okay? So go ahead and take the derivative of that, and then set it equal to 0 and find out what x's are going to make the derivative equal 0. All right, so hopefully you got the derivative is 3x squared plus 2x minus 1. Those of you who have become somewhat of a calcaholic, you should really be trying to factor that. This would be a problem where they're not going to let you use the calculator. When it's factorable, they're not going to let you use the calculator. So how does this factor out? I'm sorry?
3x minus 4x is fine.
Thank you. Three x minus 1 and x plus 1. Okay, which means x equals 1/3 and -1. Those are my critical numbers or my critical values. Now, there's lots of different ways that you can do that. You can do it like this. You could say critical numbers, and then you could say x equals 1/3 or -1. Those kinds of things. We don't have to get crazy about it, but you have to indicate that you have found critical numbers and what those values are, and then we're in good shape. Okay? Now, for part B, let's just take the derivative first, and then we'll worry about the potential undefined values. Okay? Because that's how this is always going to go. So go ahead and take the derivative of part B, please. Anything special I'm going to have to use for part B? What?
Product rule?
Product rule, thank you. Here is how you differentiate it, which how you should have differentiated it. You could have had these flipped again too. The derivative of this is 1 over x. Derivative of this, -2 x to the -3 times natural log of x. Now I'm going to simplify this a little bit because that makes finding these critical values easier, right? So that this x to the -2 goes down. I change this plus to a minus. This x to the 3rd goes down. And what that allows me to do then is think of it as one fraction. Okay? Any questions about that? Now, what I'm really then having to ask in order to find the critical numbers is I need to set that whole thing equal to 0 since the denominators are the same. Well, in order for a fraction to equal 0, what has to be true? Well, yes, the bottom cannot equal 0, but what else? The top equals 0, right? 0 divided by anything. So in reality, what I'm doing is I'm solving the top. Okay, so I've got to get the natural log by itself. So here I'm going to subtract 1 and then divide by -2. So the natural log equals 1/2. Should be positive, shouldn't it? Yeah, it should be positive.
Wait, no.
Minus 1 divided by -2. Okay? So then, what is x? E to the positive 1/2. 1/2. Yeah, I got to get rid of that minus. That's wrong. E to the positive 1/2. So that's one of my critical numbers. Is there a value that makes f of x undefined? 0, right? Because this is really 1 over x squared. Okay, so if x equaled 0, then I would have 1 over 0, which is undefined. So my other critical number is 0. Okay, and we're going to talk about what makes them critical numbers here soon. I can't tell if that's going to be today or not.
Wait, why is it 0?
Because if I put 0 into the original function, because this is really 1 over x squared natural log x, or natural log of x over x squared. And so if x equals 0, this would be undefined. This is an undefined value. All right, move on to the next thing. All right, to find absolute maximum and minimum value of a continuous function on a closed interval, here's what you're going to do. And I know you have all this in front of you, but the first thing you're going to do is you're going to evaluate f at the critical numbers in AB. So you find the critical number, and then you figure out what the f value is at that number, okay? Because a maximum and a minimum value will occur at the critical numbers or the endpoints. Then the second thing that you're going to do is you're going to evaluate f at the endpoints. This is giving us the value of the function at those points. So we're finding out what the value of the function is at each critical number and at each endpoint. And that's how we're going to decide what's a maximum or min when we're not given a graph. Because you're not always going to be given a graph. Okay? Then the largest number is the absolute maximum, and then the smallest number is the absolute minimum. Right? That's what this is. That's what's going on here. So these are the last two problems that we're going to do. And so these sometimes take a little bit of time. So you should have these. Okay? Find the absolute maximum and absolute minimum values on the given interval. What's really important as we go into these problems, okay, if the critical numbers that you find are not in the interval, then a max or a min cannot occur at that critical number. It's very important when you do these problems to make sure that the x values that you use are on the interval that you are given. Okay? So, what we need to do is we need to find the critical numbers. Now, are there any values here that will make f undefined? I can pick any x, plug it in, I'm going to square it, and I'm going to get a number. Really, the undefined things, you're really looking for fractions. Okay? How about over here? Is there anything that could make this bottom 0?
2 and -2.
That'll make it 0.
That make the top 0?
No, yeah.
See, the bottom is plus. So this whole thing that I'm covering out right now is a positive number. Doesn't matter what you plug in. There's no way that it could be. Yes, we're using real numbers today. Yeah. So we have no undefined values for either one of these. So what we need to do is just find the critical numbers. Okay. So go ahead and differentiate this. Let's just work on A for right now. Go ahead and differentiate that. And let's see what you get. All right. So, yeah. So the derivative is going to be this. Don't forget your chain rule piece. All right. So this is just regular power rule, but then I have to take the derivative of the inside function, which is 2x. So in reality, what we get is that if I simplify it a little bit, simplifying them, it usually makes it easier to find the zeros, okay? So the 3 times the 2x, 6x, and then I have the x squared minus 1 squared. All right, now I got to find the zeros. What are the zeros going to be? What are the critical numbers going to be?
0.
And 1 and negative 1, right? Because this is going to give me my 0. I could put plus or minus 1 in here. So critical numbers are 0 and plus or minus 1. Now, fortunately, one of my endpoints is negative 1, so it's going to save me a little bit of work. But what I have to do next is I have to plug in all 3 of those values and 2 into f of x and figure out what one is the highest number, which one is the smallest number. Okay? And then we'll know what the absolute max and the absolute min is. And so what I've set up here is basically a little table, and I should have put the endpoint on there too, but I suppose I want it to be suspenseful. And then I said, don't forget the endpoint. And then I put it. Okay? So that's one of the things. That's something you will forget. That's a mistake that people make, is they forget to test the endpoints. And again, the reason I didn't write -1 down is it was already taken care of by my critical numbers. So now what I want you to do is find out what these values are. Do that now, please go. Phew. Run out of time. All right. So those are the values you should have gotten. Okay, and then from there, it's just a matter of going, all right, which one's the biggest one, which one's the smallest one? And so the absolute minimum is going to be -1. The absolute maximum is 27. And it occurs at 2 and it occurs at 0. Again, it's possible that it can occur in more than one place. All right, I'm gonna save you the trouble for the next one, and because we're running short on time. But I would take the derivative, as we've already discussed. There are no values that are going to make it undefined, so I would need to use the quotient rule here to take the derivative of that function. Okay, and if I were you, I'd wait till the end. Don't try to keep up. All right, just trust me that I did it correctly. Let's make sure that I did. Okay, so then I expanded this. So this is low times the derivative of the high minus high times the derivative of the low, all over the low squared. Distribute this, I get 2x to the third plus 8x. And then this, I like to distribute minus 2x. So that becomes minus 2x to the third, and then plus 8x, because negative times a negative. So my 2x to the thirds cancel, and I get 16x over the quantity x squared plus 4 squared. Okay, so my only critical value is 0. My critical number is 0 because that's what makes the denominator or the numerator equal to 0. And then I have to test the endpoints. So I'm testing 0, -4, and 4. Plugging those in. Okay, when I plug 0 in, I get -1. When I plug both -4 and 4, I should get the same value because I get squared when I put it in. Okay, so in both cases, it's 3/5. And so my minimum value is -1, and both of those are absolute max. It occurs at more than one place, but there's still only one absolute maximum. Okay.